Welcome to Tutorial 6. In this lesson, we're pulling together everything we've learned so far by building a groundwater model from scratch. This will reinforce the step-by-step process used in every Anaqsim model. The good news? Whether you're creating a simple or complex model, the process remains the same. Every model follows the same sequence of steps. 1. Establish the purpose of your model and what you need to simulate. 2. Define your domains by recording the properties of your aquifers, clay lenses, and other geological features. 3. Create your boundaries to give your domains a size and shape. 4. Add important features such as wells, trenches, or rivers. 5. Include SVAS points where needed. 6. Solve the model. 7. Plot and analyze the results. Let's get started and establish the purpose of this model. The purpose of this Tutorial 6 model is to give you an example for building a start-to-finish simulation so that you get familiar with the Anaqsim workflow. To do this, we only need a very simple site-scale model because Anaqsim's workflow applies to both simple and complex models. This approach will give you the foundation you need for any future work. Now that we know the purpose of this model, let's open Anaqsim. Once you have it open, go to Model Input and select General. Here, we'll enter our units, set meters for length unit and days for time unit. In the comments section, type example build. Now, let's save our model by going to File and clicking Save. Next, we need to define the model domains. For this model, let's define an aquifer system with 3 domains. I should note that in practice, you would define your domains based on a conceptual model. And for complex projects, you'd likely use data management tools like Excel or GIS to organize and transfer data. But for this tutorial, you can simply copy the domain details from my screen. Go to Model Input and select Domains. Then, choose Confined and/or Unconfined from the drop-down menu. You'll see an input table appear. We're creating 3 domains in 2 distinct zones. The outer domain, which represents a zone for the broader aquifer that is far away from our area of interest and consists of a single layer. In practice, this outer domain is used in site-scale models to represent areas where we have limited data, as most site-scale projects focus on the immediate site footprint. However, placing the model boundaries too close to the site footprint can create artificial boundary effects that impact the simulation. To avoid this, we include this single-layer outer domain. The site domain upper, representing the top layer of the 2-layer zone within our area of interest, which we'll refer to as our site. The site domain lower, forming the bottom layer of the 2-layer zone. Go ahead and copy the input values from my screen. Notice that site domain upper and site domain lower are on levels 1 and 2, respectively. Since the outer domain only has 1 layer, we assign it to level 1 as well. When selecting domain type, choose Unconfined for both the outer domain and the site domain upper, since these layers start in an unconfined condition. For the site domain lower, you can choose either Confined or Confined Unconfined, depending on whether the simulation might cause water levels to drop below its top boundary. If you're unsure, Confined Unconfined is a safer choice. Finally, set the average head values the same across all 3 domains. This only serves as a reasonable starting estimate for the Anaqsim calculations. The final simulated heads will be based on your model setup. Now, click File and Save. Now that we've established our domains, we need to define their size and shape. Anaqsim supports the 3 common boundary conditions used in ModFlow and FeeFlow, and we could create our model boundaries using a combination of these. However, for this tutorial, we'll use the HSEG boundary generator again, because it allows us to set up boundaries much faster and is particularly useful for site-scale models. We'll cover more advanced boundary conditions in future tutorials. For now, let's proceed by setting up the outer domain boundary using the HSEG boundary generator. Go to Model Input, select Line Boundaries, then choose Head Specified External with Gradient from the drop-down menu. In the input table, choose the outer domain, set the XY coordinates to 0, 0, and for simplicity, set the flow gradient to 0. You can always adjust this later. Click File and Save. Next, we need to define the size and shape of the site domains. To do this, we'll use Anaqsim's built-in digitizing tool. Go to Make Plot and select Model Elements Only. Then, adjust the snap settings by going to Snap Settings and enabling Snap to Grid. Now, let's digitize a circle with a radius of 400 meters, creating a circular site domain spanning 800 meters. Click Digitize, choose Circle Polygon, and select 10-sided polygon for sufficient resolution. Place your cursor at 0, 0 and left-click, then move to 0, 400, and left-click again to finalize the shape. Click OK to save. Now we'll assign these boundaries in the model. Go to Model Input, select Line Boundaries, and choose Interdomain. Assign a label, then define the domains. Since we digitized counterclockwise, the site domain upper and site domain lower go in domain left, while the outer domain goes in domain right. Finally, paste the coordinates we just captured and save the file. Before we move on, I'll just say that while we used circles to create the boundaries for our two-layer zone, you can use any shaped polygon. Our next step in the workflow is to add the important features we want to simulate. We'll keep it simple by adding 3 pumping wells within the site domains. Go to Model Input, select Pumping Wells, and choose Discharge Specified. Create 3 wells, assigning them to either the upper or lower site domain. Place them near the center so we can easily capture them in a small SVAS polygon later. Copy the values from my screen, then save your inputs. The next step in our workflow is to add SVAS points. In this tutorial, we'll add SVAS points using all 3 methods, but we'll do it in 2 steps to better observe the effects. First, let's apply domain-wide SVAS. Go to Model Input, Area Source Sinks, and select Spatially Variable Domain. Define SVAS for the outer domain and site domain upper. Since the site domain upper and site domain lower share the same footprint, Anaqsim will automatically project these points to all stacked layers. Copy the spacing values from my screen, then save. Next, we'll add Well Basis SVAS. Go back to Area Source Sinks and select Spatially Variable Well Basis Points. Set max node spacing to 30 meters, points per circle to 6, and then select all 3 wells. Click File and Save. Now let's solve the model and analyze the results. Click Solve in the top menu bar, and the Run Log screen will appear. This model should solve in less than a second. The run log provides useful details about the calculation process, such as the number of equations and iterations used to reach a solution. This information is helpful when refining your model, especially as you add complexity through iterative design. Now let's check the results. But before plotting, we need to ensure that all details we want are displayed. Go to Plot Input, select What to Plot, and check the boxes for contours, SVAS polygons, and under Elements, choose Elements with Details control points. Then click File and Save. Now let's generate the plot. Go to Make Plot, select all selected features, then choose Level Time, Level 1, and click OK. You'll now see concentric rings forming around the wells, indicating groundwater flow toward the center of your model, right where we placed our 3 pumping wells. The HSEG boundary is also visible, outlining the outer domain, while inside, the circular subdomain represents our stacked site-scale aquifers. You'll also notice cross marks throughout the model. These are the SVAS points, and they appear denser in the site subdomain, where we set a higher SVAS resolution. In this first part of Tutorial 6, we built the foundation of our groundwater model step by step. We defined the model's purpose, established domains, created boundaries, and added important features such as wells and SVAS points. Finally, we solved the model and visualized the results, ensuring that our setup is working as expected. In the next part, we'll take our analysis further by refining our model, assessing the leakage factor, and performing advanced validation checks. See you in part 2.